Greetings, mathophiles, and welcome to a discussion of the relationship between signs of derivatives and the increasing, decreasing, or perhaps constant behavior of their original functions. We're going to begin on Desmos at a sort of graphical and intuitive level, and we're going to then proceed to some formalization and ultimately to a proof of a theorem. So we have here sort of a generic cubic, f of x equals x cubed minus 3x squared minus 9x plus 10. And I have a point that I can slide around by means of a slider. And I'm going to include as well the tangent to the function, tangent line to the function at that point, that value of x equals a. And you will see that if I stay over here on this interval where the function is rising from left to right, plugging in bigger x's yields bigger values of the function, it is always the case that the tangent line is positively sloped. And if you look over here, you can see the actual numerical value of the slope of that tangent line. The minute I click over into this interval, where we would, I think, intuitively say that the function is decreasing, the values are becoming less as we move to the right, the slopes of the tangents, i.e. the values of the derivatives, are negative. And then finally, as we sort of round the bend down below there, and we find ourselves on another interval where the function is increasing, the tangent lines again have positive slopes. And so the question before us is, can that be relied upon all the time? Can we presume that wherever a derivative is positive, its associated function is increasing? And so we'll switch over to the document camera and we'll take a look at that in more detail. If we're going to formalize a relationship between signs of derivatives and the increasing and decreasing behavior of their associated functions, the first thing we need is a good understanding of what it means for a function to be increasing or to be decreasing. So here is the definition. If f is defined on an interval and x1 and x2 are any 2 points in that interval, f is increasing on the interval if x1 less than x2 implies f of x1 less than f of x2. In other words, lesser values of the input variable give you lesser values of the function. Greater inputs give you greater outputs. That's the case that's pictured here. You see a function that is increasing under anyone's intuitive definition of what that would mean. And we find that when we plug in a lesser x, we get a lesser value for the function. And if that's true for any two x's you pick in the interval, then we'll say the function's increasing. We're now ready to state a theorem that relates the signs of the derivative to the increasing, decreasing, or constant behavior of the function, and here it is. If f is continuous on closed AB and differentiable on open AB, then the following things are true. If f prime is positive for all x in the open interval, then f is increasing on the closed interval. If f prime is negative for all x in the open interval, f is decreasing on the closed interval. And finally, if f prime is 0 for all x in the open interval, f is constant on the closed interval. If you're an AP Calculus student and you're worrying about getting the opens and closes right on the free response questions, you can rest assured that that's not really a thing that you need to be all that worried about. Historically, the exam development people have either written the questions in a way that gives strong guidance, or they've accepted either an open or a closed interval in these cases where, strictly speaking, it probably should be a closed interval. So it's good to know that the derivative sign condition only has to hold on the open interval for the conclusion to be true on the closed interval. But as a practical matter, taking the test, it's not a thing you need to worry about. Now, your teachers may worry about that, but it shouldn't be an issue on the AP exam. So let's go ahead and prove the first part of this theorem with the understanding that the proofs of the other two are going to be very similar in spirit. So we're going to be on some closed interval AB. x1 and x2 are values in that interval. x1 is less than x2, and f is going to be differentiable on the open interval and continuous on the closed interval. And because f meets those conditions, it's eligible for the mean value theorem. So by the mean value theorem, the following thing is true. There exists at least one C one number c, in open x1, x2, such that f prime of c is equal to f of x2 minus f of x1 all over x2 minus x1. Now, we were proving the first bullet, which said that a positive derivative gave you an increasing function. So let's let f prime of c be positive. So f prime is positive. x1 is less than x2, so x2 minus x1 has got to be positive. So I have some number divided by a positive number, yielding a positive number. What's got to be true about that numerator over there on the right? It's got to be positive. So f of x2 minus f of x1 has got to be positive, which means f of x2 has got to be greater than f of x1. But now we have a situation where a lesser value of x has produced a lesser value of the function, and that, my friends, is the definition of an increasing function. So, positive derivative on the open interval, increasing function on the closed interval. Negative derivative on the open interval, decreasing function on the closed interval. Zero derivative on the open interval, constant function on the closed interval. Those last two follow immediately in a very similar fashion to what we just did for the increasing function. So I hope this has helped to sort the details of this for you a little bit. Conceptually, it's very intuitive, but it's good to know the ins and outs a little bit analytically as well. Hope it's been enlightening. Happy mathing.